Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're talking about oxidation and reduction, redox. And in particular, I want to draw attention to the standard reduction potential table, which comes with the paper 2. And for some reason, they always print two tables, one with lithium and the metals on top, and one with fluorine and the non-metals on top. You can take the one with the fluorine and just chuck it away because you're not going to use it. So we stick to the one with the lithium on top. And we're going to incorporate in this explanation question 8 of the 2018 paper. So let's just give you a general introduction to what this table is about. Well, you'll see it's got a whole lot of elements, and I haven't drawn them or written them all because they're on this table, but just the few that are going to be used in this particular question 8 of the 2018 final matric South African CAPS physical science paper, the paper 2. And they always give you this table. Now, what does this mean? Why do they give you a voltage there? They give you a half reaction, reversible, lithium metal ion plus an electron goes to form lithium metal. Now, this is a big story, so let me just dive in and start anywhere. These are the metals on top. Hydrogen's an honorary metal. It sits in the middle with a voltage of 0. The real reactive, you could call them real sexy metals, are at the top, lithium being the most reactive one at minus 3 volts. Now the minus means that if you have a half reaction with a negative, that means it's not spontaneous. It doesn't want to do that. If we reverse the reaction, we said lithium metal goes to form lithium ions, positive ions, plus an electron, then that would be the way that it really wants to go. So lithium is dying to give away an electron. So slightly less so is zinc. Notice that was a voltage of 3. This is a voltage of 0.76. So that's less than 1 volt. Zinc wants to go to form zinc ions and 2 electrons. Now, zinc and lithium are metals. You know what metals look like. They're shiny, they're bendable, malleable, ductile, and so on. They conduct electricity. So that's what these metals look like. And then at the bottom, we've got our non-metals, which are the things that are not shiny, not metallic, they don't have their clink, they don't conduct electricity, etc. So we've got fluorine at the bottom. Now notice that this here, as it is written, it's gaining electrons. Now, anything that gains electrons is called reduction. But if we reverse the reaction, lithium losing electrons, that's oxidation. Now, metals like to lose electrons. They like to be oxidized, so that's why they're negative here. But if you go to the ones that are positive, these are the elements that like to gain electrons. Look, even copper, 2+, plus an electron goes to form Cu, 1+. And there's a positive voltage, it means it likes to do that. Here is copper 2+, plus 2 electrons goes to form copper metal. Now we know what copper metal looks like. That's your copper in your plumbing or in your coins and so on. So here it's positive. Copper likes to gain electrons. And then you find all the non-metals generally, or most of the non-metals, like to gain electrons. Therefore they have a positive voltage. This positive says this is the spontaneous way that it likes to go. For example, fluorine gas likes to gain 2 electrons to form 2 fluorine negative ions. That is making fluorine happy. So all those at the bottom like to be reduced and gain electrons. So some at the ones at the very top like to lose electrons the most. I always think of electrons as like E-bucks or money. Consider these metals at the top as the sexiest men, the most attractive men. The ones who like to give, they're very generous, they're good looking, and they like to give their E-bucks away. They like to pay the bill. So if you're eating with them, they're the ones who will reach for the wallet quickly and pay the bill. So they're good looking and they're generous. They like to lose electrons. Now, I tend to think of the non-metals as the ladies. They like to be have their dinner paid for. So they, and the most attractive ladies, they're always getting the most e-bucks. So please don't call me sexist. Don't write to me. Don't complain. A way of remembering. ME, metals, is the first two letters is ME. Metals I think of as men. Non-metals I think of as women. And for the case of remembering it, let's think of the sexiest woman, F. Let's think of Megan Fox. Let's think of the sexiest man, Liam Neeson. L-I, Liam, F, Fox. Let's think of her as very foxy. She likes to gain, and just a natural, let's say, state is she likes to gain electrons to form 2F minus. It's just a way, it's a mnemonic, it's a way of thinking of chemistry. We always like to talk about chemistry between men and women, so let's talk about chemistry between men, metals, and women, non-metals. Let's use that analogy. Okay, so you will find these at the top will be the ones that are quickest to give electrons. These at the bottom are the quickest to gain electrons. And in the middle, they kind of hydrogen. You can see it's got a voltage of 0 to gain or lose electrons. Now they have a question, the question 8 paper. You have an iron nail and you have a copper piece of metal in a beaker of water, and they ask a question, which one is going to rust first? And they expect you to go to this table and to have a basic understanding of what this table is about. Now, if you know that when things go from Fe to Fe2 plus or Fe to Fe3 plus, that means the iron is going from metal to either dissolving or oxidizing or forming rust or forming salt. So it's not looking like a metal anymore. Which of these here is going to want to fall apart, give away its electrons, in other words, be oxidized, the most? So now we're supposed to go to this table and we're supposed to find the two elements involved on the table. So here's copper, but unfortunately there's 3 coppers on the table. So they don't tell us which one, but they do give us a hint by saying in this question, they say that it forms iron 3 ions. So it forms iron 3 ions. Now there's the hint. That means ions with a valency of 3. So which of these has got a valency of 3 ions? There we see it. That is what that 3 in brackets means. That this is the reaction involved. So there's our 1. And now all the coppers are below. And here's the one that I'm going to choose. Why? Because we have a copper metal. There's a copper metal. That's not a metal, that's not a metal, that's not a metal. So the half reaction must involve copper metal, and then I presume it goes to form Cu2 plus 2 electrons. So all the coppers are below the iron. So which ones will give away the electrons and fall apart the fastest? Well, if we've got the coppers below, the iron is going to fall apart, oxidize, and the copper is going to be less likely to do so because it is lower down on the table, but we don't say that in our answer. We always talk in terms of it is less likely to oxidize, or it is a greater reducing agent. Likes to be reduced or gained electrons. It's a greater oxidizing agent. So we got these terms. If something is oxidized, it's a reducing agent. If something is reduced, like this, it's an oxidizing agent. So you've got to get used to the terminology that if it's oxidized, it's a reducing agent. If it's reduced, it's an oxidizing agent. What is oxidation? Loss of electrons. What is reduction? The gaining of electrons. We've got to become comfortable with the language. So now we've decided it is going to be the iron nail because it's higher up, likes to oxidize, stronger at oxidizing. It is going to be the one that corrodes and rusts first. Now they've got another question later on where they've got an iron pipe and they've got copper and they've got zinc. So they ask you, should Q be made out of copper or zinc? So here's the three that are involved: copper, iron, zinc. And they have buried in the ground an iron pipe attached through a connector to Q, either zinc or copper. Now, the question is this: if something's going to be oxidized, something's going to be reduced. That's why redox is always one word. Now, if it's highest up the table, in other words, likes to oxidize, it is the one that's going to fall apart. So what must the Q be made out of to prevent the iron from falling apart? Well, Q must be higher up the table. It must be the one with a greater oxidizing potential. So are we going to choose zinc or copper? Well, if we choose zinc here, the zinc will fall apart and preserve the iron, because the zinc will give its electrons to the iron. It will be oxidized, the iron will be reduced. If the iron is reduced, gains electrons, it stays as iron. So by burying a piece of zinc in the ground attached by a wire to a piece of iron, it prevents the iron from rusting by having something that is a better reducing agent buried with it and connected. Now they do that in geysers. In your ceiling, there's a geyser. It's got a thing called a sacrificial anode. It's normally made out of magnesium or aluminium. Magnesium and aluminium, because these are higher up the table. They're like zinc. They're higher up the table. They like to oxidize. They are strong reducing agents, and they sacrifice themselves. They lose their electrons. They slowly wear away, and this sits in your geyser. Almost the same situation as this. Here you have a sacrificial anode of magnesium. And as long as this thing is working, your iron geyser doesn't rust. Now, what most people don't know is that these sacrificial anodes only last for 5 years. That's why your geyser is only guaranteed for 5 years. So every 5 years you must change your sacrificial anode and put in a new one, because it's corroded, it's done its work, it's given away its electrons, it's fallen apart, stopping your geyser from rusting and then bursting in your ceiling, destroying your carpets. Big insurance claim. So this is a question, nice question. I like the questions from last year's paper, whereby they're actually bringing in a bit of useful information. So choose a metal that's higher up, that likes to give away electrons, likes to sacrifice itself, likes to be oxidized, so that it keeps the iron from oxidizing and therefore rusting and falling apart. So that is the answer to your question. You're going to use zinc rather than copper, because copper will not oxidize easily. It's therefore not going to protect the iron. In fact, the iron's going to give to the copper and it's going to fall apart if you used copper here, because the iron would be sacrificing itself to the copper. It would like to give away electrons more than the copper does. So that's why you would use zinc, or in a geyser you use magnesium or aluminium sacrificial anode.